Here's what we're looking at. We know that we have, let's say we have a container. Let's say we have a container. This is a box. Okay. And let's say we put energy into it in some way. Doesn't really matter how. You could shine light into it, or you could put electricity through it. Somehow there's some input of energy. I'll just use a jagged line to indicate that. So if we zapped it with electricity, or if we shine really intense light into it, some of these atoms are going to absorb that energy. And what ends up happening is that they absorb the energy and then they emit light from that. It glows. So that let's say this is hydrogen inside here. In the box. So it absorbs energy, and then we see energy coming out in the form of visible light. Light. It's emitted. Well, hydrogen, as an example, emits blue light like this, but it also emits other colors of light as well. So this particular one would be blue. But we'd also see, I don't have a red marker, but we'd also see red. And we also see purple. So we see different colors of light coming out from that same sample of hydrogen. And how do we know that we have these separate colors? Well, we don't see them as a flash of purple and a flash of red and a flash of blue. All these colors are actually combined into one combined color. And that combined, for hydrogen, that looks sort of like a pale purple. It's a mixture, though, of red, blue, and purple. So let's imagine that we have that. Let's imagine we have that beam of light here from hydrogen. What we do to figure out what the colors are is that we pass that light first through a slit. So that it comes out in a more narrow beam on the other side. Because actually over here, it's all over the place. There's light, beam would be impinging all over, but we really want a narrow beam to come out so that then we can pass that through a glass prism. We pass that through a triangular piece of glass, and that causes it to break up into what would be a rainbow of colors. If we put regular light from the sun through there and we pass it through a prism, we get a rainbow effect. But with hydrogen, we don't get a rainbow. Instead, we just get three colors coming out. They get turned, so we get a blue, we get a purple, and we got a red. And so they get separated. When those separation of those colors, when we shine them on a screen, if we also put a screen here, we're going to see those colors as lines. So there's a line here where the red would hit. The line will be the same shape as the slit that it passed through. We've got another line where the blue is going to hit, and another one where the purple hits. Okay, so we'll get just 3 lines that we can see from that on a screen, and this is called the line spectrum. So what does that tell us? Well, basically it just tells us what I already wrote up here, that hydrogen emits just 3 colors instead of emitting a whole rainbow of colors. All right, so here's the explanation for that. So the explanation for the line spectrum really is a theory. Remember, theories explain things. And this is the explanation is Bohr's atomic. And this was a breakthrough at the time, but this is an old theory, and it's a good example of the fact that theories actually can evolve and they can be replaced by other theories. But it's still a good tool for us to use because it's a simpler view of the atom than the modern view. So that's what we're going to start with, is Bohr's atomic theory, the Bohr model of the atom. I know that's not focused very well, but I think you can still read it. Bohr model of the atom. It builds on Rutherford's model, which has a nucleus in the center, and for that nucleus, and then it has electrons that are orbiting the nucleus. So let's just put, for hydrogen only has 1 electron, and that was known at the time. So you have a nucleus and an electron, and the electron is moving in an orbit. Okay, like that. Now that part alone isn't really new. Even Bohr would have, even Rutherford would have had that model. What's new though is that electron can only be at a certain radius from the nucleus, which means only a certain energy from the nucleus. So it can be here if it's at its lowest point, but it can't go any closer to the nucleus than this. This is no man's land. It can't exist in here. But it can exist further out, but not in any position further out. It could exist here, though. So this could be another orbit of the electron. So what we So this is an orbit, and so is this. Both of those orbits are possible. Okay. This location, though, this is not possible. For the Bohr atom. So that's not a possible orbit in the middle here. Hey, I didn't even draw it, but it wouldn't be possible for it to be there. It can only be here or there. There's more than those, though, because there could be an even larger radius here. Okay, and this would be another orbit. Both of those are orbits. Those are all three of those that I drew in dotted lines are possible orbits, but you can't have anything between them, at least not in terms of the Bohr model. You can't have the electron existing in those locations. And then those locations also then define the energy of the electron. So you have fixed orbits, fixed energies. That's the hallmark of the Bohr model of the atom. And I'll show you in a second why that explains the spectrum. These are fixed orbitals. Or sorry, orbits, not orbitals. Fixed orbits. And fixed energies. And that combination, when you have fixed orbits and fixed energies, we say that it's quantized. So the Bohr model of the atom gives us quantized energy levels, quantized orbits. That doesn't mean it can't move from the orbit, but it means that if it does move, it has to go to another fixed orbit and fixed energy. So let's say my electron, instead of being right there, moving around, let's say it's out here. And it would have gotten there by absorbing some of that energy that I showed going in the box, that jagged line. So it might exist up here at some point. If it exists up there, it doesn't really like being there because that's what's called an excited energy level. And most of the time, atoms and molecules don't like to have their electrons having those excess energies. So the electron wants to fall back down to where it's more comfortable. And when it does that, let's say it does that here, it can fall back down and then continue its orbit there. But when it does that, it has to emit the energy that it contained in that at that level. And so the only way for it to do that, since it's not interacting with anything, it's just falling down on its own, the only way for it to get rid of that energy is to emit the energy in the form of light. So that's where we get the photons. This transition, get a light. But the light is a very fixed energy. It's a very particular one because there's only certain energies that can be involved here. So this light would be a photon, and it would be one color, or one energy. So that can be going on all over the place in the Bohr model of the atom. The reason it explains our observation, though, because if you remember that previous picture that I had where I showed red, purple, and blue light coming out of the box. And we saw that because we split it with that prism into the spectrum of colors. Those three lights are only possible because hydrogen only has certain energies that will give visible light, certain transitions. They're called transitions. This is an emission. The light coming out is an emission. Going from one level to another is a transition. So the electron undergoes a transition, then it emits a photon of light in doing that. So we're going to look at the same thing overall, but with a slightly different point of view that makes it easier to see the energies, because this picture only shows the distances. We go to a picture that shows energies, then we can see exactly where the different colors come from.